on recent trends in intelligent systems. The session will be continued by Dr. G. Kiran Kumar sir. Sir, well, once again, I welcome Dr. G. Kiran Kumar sir. Please take over the session.
Thank you, ma'am. Welcome back to the session and continue the morning topic. In continuation of that, ambient intelligent systems. In this session, we select one particular kind of system model. And further, if you want to add artificial intelligence, how it will be equivalent to ambient intelligent system. The capability of analyzing and the decision making capability. How we can make that more robust. As a part of considered system model, so three things we need to combine. One is cooperative relaying, second one is normal technology, the third one is Swift technology. So combinedly, with assistance of these three technologies, can form a new system model, which is an example of next generation wireless networks. If you change the frequency, it will be next generation wireless networks also, not only 5G, 6G also, beyond 5G also, depending on operating frequencies and all. We can address these problems with the smartness we have with the network. So as a part of that, we'll discuss now. Think, is this visible?
Yes, sir.
Yes. So we are proposing a system model with the combination of three. So the basic about these three we will discuss here, then we'll get into PPT. Then we see the slides, we come to know what each technology will gives you and what is the significance of each technology for the system model and how to continue and how to address the research challenges in this particular system model. As a part of that, the first technology we are using in the system model is cooperative relaying. The second one is normal technology, non-orthogonal multiple access technique. The third technology is Swift technology. Simultaneous wireless information come power transfer. So the simple another meaning of this is energy harvesting, Swift technology. So we are combining these three and we are proposing a new system model. For this system model, we are adding some smartness, intelligence, and decision making. So here we can monitor the system, we can analyze the system, and we do the decision making also. So that becomes smart, cooperative relaying, and NOMA. And the Swift technology assisted IoT network, we can frame it as. And we are adding some artificial intelligence capability to that. It becomes smart. And coming to the first one, what is cooperative relaying? What is the need of cooperative relaying? This is a question we need to answer first of all. And now, as a challenge of every generation network, if you keep on going from one generation to another generation, evaluation of mobile communication, first generation to fourth generation. Generation by generation keep on increasing, the number of subscribers are increasing, at the same time the data rate also getting increased. So more number of signals to be multiplexed because more number of bits to be transmitted such that high data rate you will get. So that is possible by transmitting many number of signals with multiple antennas. The system we used to call it as MIMO system. Multiple input, multiple output antenna system. More number of antennas at the transmitter, more number of antennas at the receiver is required. The number is big. Now in 5G, we can call this as a massive MIMO. More number of antennas, the number should be large. More number of transmitting antennas, more number of receiving antennas. But equipping more number of antennas with the single node. Let us assume a simple network of 3 nodes. This is a source and a destination. And you are equipping source with many number of antennas. It is MIMO system. Again, it is a problem to have many number of antennas here. Establishment of these many number of antennas is difficult. How to provide isolation between these antennas, how to differentiate these antennas is very big task. So there is an interference between these antennas because they are located on the same transmitter or receiver with respect to same node they used to be established. So their implementation is not cost economy. At the same time, interference problems we used to get. It is very difficult to differentiate all the antennas we have, which are located with respect to a single node. So many other problems we have, especially in resource allocation also. We are limited in resources. That also a problem for this MIMO system. If keep on increasing the number of antennas, the problem of differentiating these antennas with respect to their generating signals is very difficult because their operating frequency should not be same. At the same time, their operating location also should not be same. Many other difficulties are there. So there is a proper alternative for this. Because surely we need MIMO system because we need high data rates. Otherwise, we need to have more reliability of the transmission. Means data surely have to reach the destination. There's a guarantee. If you are depending on only one direction, one path, only one particular channel, reliability of the transmission will not be proper, will not be sufficient. So in those cases, surely there is a need of MIMO system, but equipping each node with multiple number of antennas is not a feasible solution. In that case, what they do? So in a network, there are set of nodes. That is assumed the source and destination. Source want to communicate with the destination. They're transmitting its information to destination. Suppose the link is not good direct link, it is weak link. So it will select another node, which is a relay node, which is a helper to this source. So relay helps the source to send its information to destination. So source is sending its information via relay to the destination. There is an alternative path. But assume now here source having a single antenna, relay having a single antenna, destination having a single antenna. But we are taking now sharing of the remaining 2 nodes also. So source taking the help from the relay nodes. Actually, it has only one antenna, but it is taking the help of relay unit also. So relay antenna also getting shared by the source antenna. At the same time, source. Now physically source has one antenna, but virtually it has 2 antennas. One of its own and the second one from relay. So that means single antenna users, the nodes equipping with a single antenna, they are sharing their resources to form virtual MIMO. It is not a physical MIMO, virtual MIMO. This kind of system having all the benefits of physical MIMO system. In only one factor it is different. So no node having more than one antenna, no node having more than a fixed number of antennas. Combinedly they are taking sharing from other nodes. For source, relay acting as helping unit. For relay, source acting as helping unit. Like that, mutually they will cooperate in the transmission of original information from source to destination. If the direct link is not good, this direct link is not good, we will go for another alternative way. In this alternative way, relay helps the source to send information to destination. So this is called cooperative relaying. This is one kind of diversity technique. They are creating or differentiating the different paths. So that's why it is one type of diversity. In this type of diversity, antennas are located at different places, different locations. So it is one kind of space diversity, one kind of space diversity. So this new kind of space diversity is called cooperative diversity. Cooperative diversity. So the name itself, it tells you there is a sharing between the nodes. So all the nodes in any network will share their resources. The resources may be antennas, the resources may be bandwidth, the resources may be channels, the resource may be power. So they share the resources to form a virtual MIMO. This virtual MIMO will have all the benefits of physical MIMO. So no need of multiple antennas at each node. Even limited number of antennas or single antenna users also can communicate with all benefits of MIMO system. This is called virtual MIMO or cooperative diversity or cooperative relaying technology. So which is the replacement or alternative for MIMO system. Alternative for MIMO system. So from third generation onwards, 3GPP LTE onwards, so we have this concept of cooperative relaying. Cooperative relaying. So whenever the direct link between source and destination is not good, we will take one cooperative agent, one helping user, which is also a trans-receiver circuit. Here source is a trans-receiver circuit. It is also a trans-receiver circuit. It is also a trans-receiver circuit. Relay sending its own information. Along with that, it is sending the information of other nodes also. It is acting as a helping agent, a helping unit to the remaining nodes also. Remaining nodes also. So this is basic about cooperative relaying. Cooperative relaying. So cooperative relaying will address many problems of MIMO system. The first feasible solution it can offer is, so no need of multiple antennas at each node. Even single antenna is also sufficient to provide diversity. And one more is, it can improve the reliability of the transmission in one particular case. In another case, it can enhance the data rate also. So previously, only direct link is there. Through this channel only, we have to send the information signal. Let us assume only one copy of X, one signal only transmitted from source to destination. Let us have now a relay unit also. So an alternative path we have. We have two different paths. So the diversity order is 2. Previously only one path, now it is 2. So diversity order is 2. Over these two different paths, you are broadcasting the same information. So through this indirect path also, we are communicating X only. Through the direct path also, we are communicating X only. At least among these two paths, one path may take this information safely to the destination. So reliability of the transmission will improve because more number of relays are there means more number of alternative paths are there. Same information getting broadcasted over all the different paths. At least one path have the capability to completely assure the transmission of X from source to destination. Reliability will increase. Instead of sending same information over different paths, you are sending different information signals. Over the first path X1, over the second path X2, two different signals you are sending. So data rate is getting doubled, two different signals. Two signals are getting transmitted. Previously the data rate is only X, now two signals are transmitting, double time the data rate. So data rate is getting doubled. If you send different signals over different paths, data rate will increase. If you send the same information over different paths, reliability will increase. So these are the benefits you are getting using cooperative communication. Reliability of the transmission will improve, capacity, data rate will improve. Alternative for this MIMO system, most importantly, during the fading concept, most of the real-time channels are faded channels. So the received signal strength getting decreased due to this faded nature of the channel. So we know the basic principle of power. So a transmitter and a receiver, they are located apart. We are transmitting our information signal with a power. So the transmitted power will decrease exponentially with respect to the distance. As the distance between transmitter and receiver is increasing, the power of the signal will monotonically decrease exponentially. So the relationship we have, if keep on increasing the distance, automatically the signal will lose its energy. It almost negligible. It will not be identified with the receiver circuit. Using cooperative diversity. So the relay, based on how it responds to the incoming signal, always the signal can maintain minimum amount of energy. So there is no signal loss in this case. Reliability of the transmission always good in cooperative communication. So these are the possibilities we have. So now see how these cooperative relaying technologies will operate, how the relay respond to the incoming signal. So based on that, we have relaying protocols. So this is the relay, is the cooperative agent which is helping the source to transmit the information. We know that the direct link between source and destination is not good. It is the weakest link we know. Then we are searching for alternative node, which is relay node, which is ready to help us. Which is ready to help us. According to the basic principle, we have y is equal to hx plus n. We can represent the channel now. It is the channel between source and relay, S and R. There is a channel between relay and destination, HRD. There is a channel between source and destination. If you write the received signals at relay at a destination, it can be written as, let us assume it is the signal received at relay from source. So it is YSR. So YSR can be written as, let us assume original information signal generated at the transmitter is X. Original signal is X and it is applied with the energy of under root of PS. Under root of power is energy and the channel in between these two is HSR and the noise is NSR. This is the signal. Now the signal reached at the relay. This is the signal amount we received at the relay. Now the question is how this relay will respond to the incoming signal. So based on response of relay to the incoming signal, we are classifying relaying protocols into types. The first type, we already know it is indirect path. The signal traveled for long distance. It is almost weak because the direct path, the distance is somewhat less compared to the indirect path. If you see indirect path, the distance is more. It has to travel long distance. Now, during this journey, whenever the signal reaches the relay blindly amplifies the incoming signal and forward it. So boost the signal. So after a signal traveling for long distance, what the relay unit first do? Blindly it amplifies the incoming signal. Whatever the amount of signal it receives, it blindly amplifies and send it to the destination. Another way to say technically, we can call it as scaling of the incoming signal. We just scale the incoming signal and we forward it to the destination. This is first way of responding to the incoming signal by the relay. So first relaying protocol is AF relaying protocol. Amplify and forward. Amplify and forward. Amplify and forward relaying protocol. Now the question is, it is just blindly amplifying and forwarding. See the received signal content. We are amplifying almost this total signal by a factor beta. It is the amplification factor. The advantage is it is simple to do it. The relaying protocol easy to implement because it is just only amplifying, just cascading. But the drawback is, see the signal content we have received. There are two components. One is the signal component, second one is the noise component. So we are amplifying the signal component, it is good only, but along with that we are amplifying the noise component also. That is the limitation of amplify and forward. In amplify and forward relaying protocol, we are boosting the signal content along with the noise content. So the noise is signal component also getting amplified using this amplify and forward relaying protocol. When it will be a not feasible solution, when we cannot prefer amplify and forward relaying protocol. You see, if signal component is more dominant than noise component, no problem at all. If you amplify, yes, it is again more dominant than noise, then no problem. So whenever the situation is reversed, that means signal power is much less than noise power. Means here the noise is more dominant. Noise is more dominant. Again, you are amplifying the noise. Again, you are amplifying the noise. Means noise taking the total dominant factor. It becomes as the dominant factor. Noise becomes as dominant factor. In this particular case, it is very difficult to identify our signal component and demodulating or decoding it. So amplify and forward will not gives you better result whenever the signal component is not dominant component than noise. So that means signal to noise ratio is less value, low range of signal to noise ratio. It is not performing well. As a limitation of amplify and forward, whatever the signal we can able to receive automatically, that will be blindly amplified and forwarded to the destination. This is AF, amplify and forward. The second relaying protocol we have is decode and forward. So decode and forward. So the basic relaying protocol we have is DF, decode and forward. Decode and forward. As already discussed, there is no circuitry to completely make noise as zero. We can minimize the impact of noise, and we can use inverse channel filter. We can predict only the signal component whatever we have transmitted. From this YSR, I am estimating original signal component X cap. What is my assumption? X cap may be approximated to X. It is approximately, or otherwise X cap always less than or equal to X. It not completely equal to X, but it is a portion of that, scaled version. So that is called detect and forward. When it is possible to detect the signal component, when it is possible to detect the signal component from the received signal. Now see the expression. The received signal expression is YSR is equals to under root of PS is HSR X plus NSR. I can minimize this amount of NSR when it is possible, when the signal component is more dominant. But I assume this signal component level is 1000. This noise component is around 5. And compared to this large factor, it is negligible. So what we need to do, we need to have signal component more dominant than noise component. If you do like this, automatically we can neglect the amount of noise because signal component becomes more dominant. It is easy to detect. So the performance of decoding and forwarding relaying protocol completely based on decoding capability of the relay. When the relay is able to decode it perfectly, that means YSR is equals to X cap, where this X cap is less than or equal to or much less than or equal to X. If it will happen, then we can say the relay is perfectly decoding. Then we can transmit the same signal to destination. So decode and forward. Depending on the decoding capability of relay, we can send our information to destination with better performance. Compared to AF, DF gives you better result whenever the relay decoding it perfectly. When it is possible, perfect decoding capability of the relay, when it has highest amount of capability to detect the original signal. Whenever the signal to noise ratio is large, high values of signal to noise ratio means signal power is more dominant than noise power. In this particular case, if the signal power is more than noise power, it is high SNR range. In high SNR region, the relay has the capability to decode the signal X. So then automatically it performs well. So AF relaying protocol performs well in low SNR region, where DF relaying protocol performs well in high SNR region. These are the basic two relaying protocols we have. If you want to combine these two, we can combine and we can propose new hybrid relaying schemes also. New hybrid type of relaying schemes also there. Hybrid relaying schemes. So in this kind of thing, we can combine this AF and DF. Because AF operating well in low SNR region, DF operating well in high SNR region. You just have a threshold. So in between source and destination. So source we have, destination we have, relay we have. First check the link SNR of this one, gamma SR. If the link SNR is good, if it is greater than the threshold, that means we are operating on high SNR, select DF. If this SNR is not good, it is less than gamma threshold, operate in AF mode. You can combine these two, that we can call it as a hybrid relaying. SNR based hybrid relaying you can make, or decoding capability based switching also we can make, and you can combine AF and DF relaying protocols. You can propose it as a hybrid relaying. And another category of relaying protocols are there. Those are called incremental relayings. Incremental relaying. Incremental relaying. The name itself, it is incremental. So actually it is source to destination only one path. Check the first direct link. If the direct link is good, no need of relay. No need of relay. If the direct link is not good, then only we need relay unit. So checking this possibility is called incremental relaying. It is without relaying, first of all, it is only direct link. If the direct link is bad, then only go for relaying. If you test the direct link, then you go for relaying. If you combine these two, making a switching statement, then you can call it as incremental relaying. Incremental relaying. So without any modification, if you implement the basic relaying protocols as it is, those are fixed relaying protocols. AF relaying protocol, DF relaying protocol, they are fixed relaying protocols. So these are the basic about cooperative relaying schemes. What is cooperative diversity and what are the basic relaying protocols we discussed. So the cooperative relaying is the alternative name for cooperative diversity. It is new type of diversity. We can call it as a space diversity. Space diversity. The first one, it is solution or alternative for physical memo system. The problems we have with respect to physical memo will be overcome by this virtual memo concept. How to define this cooperative diversity is a single antenna users, the nodes with the single antenna, share their resources to form virtual memo in a network. Then you can call this cooperative diversity. The basic relaying protocols we have are AF and DF. We can make it as hybrid also. We can search for new type of cooperating relaying protocols. So many other relaying protocols also there. Differential relaying coding also there, and the coded cooperation also there. You can send with different codes of relay also. Coded cooperation also there. So different relaying schemes also there. With respect to cooperative communication, still research is going on how to select more number of relays. Relay selection is one research challenge with respect to cooperative relaying. Relay location, based on the relay location also performance will change. And how to select better relays, at the same time the duplexity of this relay, whether they are operating in half duplex or full duplex, whether it has the capability of two-way communication or not. So coming to the nature of the relay, we can improve the performance. These are the research challenges with respect to cooperative relaying. And the second part we have, it is NOMA, non-orthogonal multiple access technique. So up to 4G we have OFDM, orthogonal frequency division multiplexes or multiplexing. So we are used to combine many number of signals using OFDM. So they should have multiple carriers. They should be orthogonal to each other. Every time we need to add some cyclic prefix, and it is very complex to generate and complex to decode, separate the carriers and information signal with respect to OFDM. Most importantly, we have PA-PR ratio as the limitation of OFDM. Every time we need to go to frequency domain, IFFT is required. They need to waste some bits as a cyclic prefix, and very complicated to provide multi-carriers which are orthogonal to each other. That's the main limitation of OFDM we have. So suppose n number, the number of signals to be multiplexed is keep on increasing. 256, 64, 1024, 512. More number of carriers you are taking as inputs for OFDM. The generation demodulation is complex, and indirectly we are wasting the bandwidth. Indirectly we are wasting cyclic prefix, and most importantly we have a limitation of PA-PR. To overcome all the limitations of this OFDM and to improve the connectivity, to provide massive connectivity. The meaning of massive connectivity in multi-user network. In multi-user network, more number of users are there in network. Many possibility or more number of possibilities are there to combine any two nodes in a network. Any two nodes in a network. So that means there is a possibility of multiplexing many number of signals. Those signals to be broadcasted to all the nodes of a network. It is possible with NOMA. So the generation of NOMA is very easy. So multiple carriers may not be required. At the same time, all the signals to be multiplexed. All the signals to be multiplexed, no need to be orthogonal. No need to be orthogonal. So they can occupy the same time duration. They are operating on same frequency. In simple words, I want to or I have to multiplex n number of signals. I want to combine these n number of signals. These signals are same in time, same in frequency. They are not different to each other with respect to time and frequency. In time slots, they are having equal time slots. Their operating frequency is also same. It is one type of single carrier only. But how these signal components are different? So these multiplexed signals are different with respect to their operating powers. So they are operating with the different powers. The signals to be multiplexed should equip with different level of powers. So with respect to either different powers or with respect to different codes. We are assigning all the signals to be multiplexed with different codes or different powers. If you apply different powers to the different signals, it is a power domain norma. Power domain norma. If you are assigning different codes to the signals, then it is code domain norma. So what the basic principle of norma we have discussed, no need of orthogonality between the multiplexed signal we need to provide. So they are same in time, they are same in frequency. This is the most important thing. But they are different with respect to their operating powers. Different with respect to powers. Different power levels they have. All the multiplexed signals. So now this combination, the deadly combination is NOMA. How we can assign these different powers to the incoming signals or broadcasting signals, depending on the channel quality, depending on the location of users, we can assign power to multiplexed signals. Let us take a simple example of two-user case. Simple example of two-user case, how NOMA will be. Let us assume it is a source. From source, I need to multiplex two signals, X1, X2. These two are the signals I want to multiplex from source. There is a far user D1. There is a near user D2. So D2 is near user. D1 is far user. I'm saying it is a far user. Long distance I need to travel. So more amount of power should be allocated to far user because long distance we have to travel. Here it is a near user. So short distance I have to travel. So little amount of power is sufficient. Let us assume the power I need to apply for D1 is A1 because more power, and the power I'm applying to D2 is A2. So A1 is the power I'm applying to X1, A2 is the power I'm applying to X2. Now the composite signal, the normal signal now, A1 X1 plus A2 X2. A1 X1 plus A2 X2. I have the constraint A1 is greater than A2. A1 is greater than A2. X1 and X2 occupying same time interval. X1 and X2 operating at same frequency, but they assigned with different power levels. For the far user signal X1, I allocated a power coefficient of A1. For near user, I applied a power coefficient of A2. The relation between A1 and A2 is A1 is greater than A2. They are different with respect to powers. Now the question is, I am transmitting this composite signal. We are broadcasting this composite signal to both D1 and D2 equally. So D1 also receiving A1 X1 plus A2 X2. And D2 also we are sending A1 X1 plus A2 X2. We are just transmitting this. And we have basic principle. This signal traveled for long distance. As the distance increasing, the transmitted power will decrease exponentially. The power of the signal will decrease because distance increasing. So A1 is large power component, A2 is small power component. A2 value is small already. It is low energy component, and it is traveling for long distance. Means automatically A2 value will decrease, almost it becomes negligible. This is second factor is negligible when it reaching the destination D1. The signal component or the signal component with lowest power after traveling a long distance becomes negligible. Automatically we can have the highest energy component signal component only, that is A1 X1. The second signal, near signal or near user component will be neglected at far user because the near user equipped with low energy. That low energy will be decayed, it will be reduced and become negligible while it reaching the destination D1. And coming to the near user, if you compare, there are two components. First component with respect to far user, second component with respect to near user. Among these two components, first component is the dominant component because A1 is greater than A2. We can easily identify the dominant component easily. So we are selecting this dominant component. Apart from the dominant component, the left out component is our required component. The left out component is required component. Subtract the far user component from this. So that means A1 X1 plus A2 X2. The dominant component I am subtracting A1 X1. If you subtract this, the left out term is required user term, that is near user signal. So this subtraction is called successive interference cancellation. Apart from our own signal component, all other remaining components considered as interference components with respect to the user. So here the user is D2, his own signal is X2, where X1 becoming interference for the D2. If you are subtracting this procedure is called SIC, successive interference cancellation. Cancel the interference. For X2, X1 is the interference, cancel it, and select our original signal component. So this is. So for near user case, you are applying SIC, successive interference cancellation. So A1 X1 plus A2 X2 in this component, X2 is my required component. So cancel the another component as interference. If you do this is successive interference cancellation. Automatically you can select our component. So this is the basic principle of generating NOMA signal and decoding the NOMA signal. And coming to the limitation of this NOMA is the successive interference cancellation. The node should have perfect capability of successive interference cancellation. If it is unable to remove the signal component of far user, you will not get proper reception of only the signal component of second user. And one more thing, it is the example of two user case. Suppose I want to multiplex n number of signals, then it is A1 X1 plus A2 X2 plus A3 X3 plus and so on. It is AN XN. Now we need to differentiate all these signals. We need to provide A1 is less than, A2 less than, A3 less than, and so on, which is less than AN. They're different with the different powers. Now I want to select the last component. For the last component, I want to select. So remaining all terms becomes as interference to this particular component. Apart from my own signal component, remaining all other components becoming as interference. It is very difficult to subtract all these remaining components, select our own particular component. So successive interference cancellation will becomes a problem when the number of users are keep on increasing. You are dealing with more number of users, automatically SIC, successive interference cancellation, will becomes a bottleneck of this NOMA technology. Apart from that, the generation of NOMA is very easy if we have perfect successive interference cancellation. It is about NOMA technology. But now in 5G, most of the researchers have taken the choice of NOMA and they combined, tested for 2 user case, 3 user case, in full duplex mode, in half duplex mode. Now they are increasing the number to multiple numbers, higher values of n, and they are doing proper mathematical successive interference cancellation also. They are in a way to propose new successive interference cancellation methods. This is regarding the NOMA. And coming to the third technology we have, that is a SWIFT technology. SWIFT technology. So another name for this nowadays they used to call as green, away from radiation, green, energy harvesting. Energy harvesting. A source and destination and relay. Now relay is helping the source. It is sending its own information along with the information of source. Now what about the sustainability of the relay? How it can be maintained, and for its maintenance, where it can take energy from. So that is called energy harvesting problem we have. So what we will do here, so whatever the information signal it receives from source, the relay, a portion of the signal it receives will be harvested at the relay. It will use a portion of the energy from the received signal, use it for its maintenance, and remaining signal energy contribution only forward to the destination. So that means in the incoming signal there are two portions. One portion of the signal may be harvested at the relay, remaining portion may be forwarded. So this yellow color you can call it as harvested. Let us assume under root of PS amount of energy we are applied to the information signal X. It is reaching the relay. Now within this energy of PS, a portion, let us assume alpha times PS portion is harvested, is saved at the relay. Remaining portion 1 minus alpha times under root of PS. This portion will be transmitted to the destination. So this amount will be harvested, saved for the maintenance of relay at this. So that means in the information transmission itself, there is a power transfer also. That's why simultaneous wireless information come power transfer. Indirectly, we are transferring the power, but directly we are transmitting the information. In the information transfer itself, we can separate the power saving. That is called energy harvesting. So this technology is called as SWIFT technology. Many of the IoT devices nowadays, they are limited with energy. They need little amount of external energy from other sources. Using any kind of renewable energy, whatever may be the form of the energy. So that energy will be transmitted as information from one node to another node. While it receiving information from one particular node, a portion of the energy of that particular signal will be harvested, will be saved for its maintenance sustainability. Then this type of technology is called SWIFT technology. So no need to provide any external battery services to the nodes of a network, which are acting as cooperative agents for their maintenance and all. So they just use the information transformations only. Then how much amount of power we need to harvest and what amount of power we need to transfer to the destination. Means how to find the optimum value of alpha, how much amount of power we need to harvest. Finding the proper value of alpha is an optimization problem. Is a challenge to solve. We can able to solve this particular one to propose an optimized SWIFT technology. Using SWIFT technology, you can propose a smart agriculture, smart sensor environment, or a smart radio environment, smart remote disaster monitoring. A particular disaster management case where all the radio units are not working properly, you can use a UAV network, unmanned air vehicle, a drone kind of thing. The maintenance of drone, we can use it from SWIFT technology. It harvests its energy from the information itself. And it can create communication between unpossible receiver case to a possible transmitter case, which is an example of smart radio city. You combine these three, cooperative relaying, SWIFT technology and NOMA technology, we are proposing new kind of system model, and we are getting the research challenges with respect to that. So these are the basic about these three. Now we get into PPT, where we have this distribution and all. Just observe the things. Is it visible to all? Yes, fine. Now see, as a first part, we discussed about what is cooperative wireless network, what is NOMA technology, what is SWIFT technology. We combine these three and we are adding some smartness to the network. So that's why artificial intelligence assisted, SWIFT enabled, cooperative NOMA based IoT network. This is an example of ambient intelligence system, because in the system model, we have the ability of monitoring something, analysis, decision making capability. We used to have this. So we see the basic of NOMA and cooperative relying, and whatever things we have discussed, basic behind that, and we'll see how this proposed system model also. So see, what is NOMA in wireless communication system? Already addressed. It is a non-orthogonal multiple access technique. Why NOMA? Because we have many problems with respect to OFDM, with respect to all spatial coded multiple access techniques. Also, we have some limitations. So to overcome those limitations, to make multiple access technique much more simpler, we coming to NOMA. And the basic relaying schemes with respect to cooperative relaying, we have amplify and forward, decode and forward. Diversity combining strategies also, how to combine all these multiple copies at the receiver. So we have different patterns to combine all multiple components at the destination. So those are called diversity combining strategies. MRC, maximal ratio combining, selection combining, equal gain combining. These are the examples of diversity combining strategies. So wireless networks for IoT applications of future directions. And see, the basic principle we have explained about NOMA. Take an example for a downlink case. A base station broadcasting a composite signal. So two signals are getting multiplexed. We are adding two signals with different powers. So their operating time is the same for both. Operating frequency also same. So they are different with respect to power. See the y-axis, user 1 with the yellow color having low amount of power, user 2 with the green color, and power axis it is with the high power. So with respect to time and frequency, both are same, but with respect to power only they are different. With respect to power only they are different. So user 2 is a far user, user 1 is a near user. At the near user, user 2 signal is dominant component. You can easily subtract it as interference. You can decode the first user 1 signal as is. For the second case, far user case, no need to subtract anything, because low amount of signals after traveling for long distance automatically will be neglected. And we can directly decode the user 2 signal. This is a basic behind NOMA signal we already discussed. And if it is a multi-user environment, it is like this downlink NOMA, uplink NOMA. You want to convert for a number of users also, this is an example. We get into the things. And see the basic relaying protocols, whatever we have discussed, amplify and forward relaying protocol, decode and forward relaying protocol. AF amplify the signal component. The drawback we have is along with the signal component, noise amplification also there. There is a limitation of amplify and forward. Coming to decode and forward, whenever the signal will be decoding perfectly by the relay, automatically DF performance is better than AF. But the problem is, it is possible in high SNR region only. In high SNR means signal power should be more dominant than noise power, then only the relay has the capability to decode it. So these are the important literature we have with respect to all these three technologies. And if you want to propose a new kind of thing, combination of these three, it will be like this. Is it visible? So you can use any kind of machinery or any kind of transmitter, any kind of electronic device. You want to monitor that, keep the sensors there. So sensors sensing the working condition of any electronic device, or it's a machinery, a human kind of thing, whatever maybe, it's a remote thing. We are just collecting information of that particular thing using sensors. That sensed information will be broadcasted to the IoT relays. See, there are two arrows for every IoT relay. So here the maintenance of IoT relay. The relays may be anything. The relays may be vehicles. The relays may be mobile phones. The relays may be drones. So they are getting their energy They are getting their energy from the information itself. Let us assume the green color indicating energy harvesting, a portion of the signal to be saved by the node. And the yellow color is the original information to be transmitted, the original signal to be transmitted. So here we have relaying, where the direct link is not good between source and destination. That's why we are taking the help of relay units. We are taking the help of relay units. So these relay units will get energy benefit from the signal transmission itself, and the remaining portion will be broadcasted to users. Let us assume there are NOMA signal, near user, far user. D2 is the far user, D1 is the near user. So to these two different users, we are sending information. Multiplexed signals are there, diversity combining strategies, IoT users. We can send this information after reaching the destination and all to the router gateway. We can save an IoT cloud. The cloud data may be used by any particular kind of users. They have the capability to control the sensors again. They can control the transmitter again. If you want to make a loop, you can make a loop from cloud to users and from users to sensors. Because after taking the information from IoT relay to the destinations and all, we can analyze the data. We can analyze the data, and we have decision making capability, smartness also there. So with the cloud data, whatever we have, we can take some decision. We can activate our actuators. We can control the transmitter again. This is a system model we have. The system model we have. So this is the new kind of system model which was not proposed earlier. The combination of these three. Those who want to do the research, they want to start. Take it as a simple example of new system model kind of thing. You can form a loop also. From IoT cloud, you can make a loop to the sensors again. You can frame a actuators. It is simply an example of cyber physical system. You can apply it to a smart agriculture case. So here the sensitive information from a smart agriculture land. It will be a wireless sensor network, or otherwise it is a simple smart radio environment, is a smart cellular network, or otherwise a smart intra-terrestrial, from underground to outside free space, or underwater to outside free space, or it may be a satellite for remote disaster management case also. So any kind of smart network, these three combination will be a feasible solution. This is a block diagram about the connection of system model with the three technologies. So here we have cooperative relaying at the relays. With respect to D1 and D2, we have NOMA technology. Different signals are multiplex. And coming to here, energy management of these relay nodes is coming from SWIFT technology. So this green and yellow indicating SWIFT technology, D1, D2 indicates NOMA technology. The relaying units cooperative diversity. So three technologies are involved in this system model. You can propose a new kind of system model with the help of this. You can replace this relays by a vehicle, a mobile, a drone. If you go just beyond this, these relays will be again simple sensors again. A smart remote health caring system also. You can replace this relay by simple sensor units. That also a possible solution. Now this is up to system model only. So what kind of future challenges we have and how to deal with this particular system model? These are the steps we have to deal with this system model. First of all, we framed the system model as morning class we already discussed. Then we do performance analysis in terms of similar rate or channel capacity or probability. Optimize the problem, find the solution, compare with the existing schemes, experimental validation, which is nothing but our FPGA design. So if you do this, it will give you surely a better result. And some simulation parameters, those who want to do simulations, this kind of parameters we need to take as input to. For our case, we have chosen like this. So those who want to do this kind of simulation parameters, you can take and test the performance of this system model, which is the combination of three technologies. And those who want to continue, for them research challenges are the resource allocation, how to allocate different powers to these nodes. You can take it as one challenge. How to select these relays, their location optimization. If it is UAV, proper location of UAV or range optimization. That also you can do as a research challenge. Channel estimation, because we are assigning power to the nodes, whether it is a near user or far user. Importantly, in real time, no device location is stationary. It is not fixed. Every time the location of users will change dynamically. So with respect to the location of destinations, we are automatically, dynamically change the allocated power. That's the biggest challenge of NOMA technology we have. How to deal with this? The dynamic change of location of users, how to trace that, how to allocate different powers that you can estimate from the channel estimation or the channel prediction or quality of SNR. So relay unit selection, optimized Swift technology, optimized NOMA technology. And if you are you can do physical layer security also. D1 and D2 are authorized users because it is in free space. It is in free space. Some unauthorized users also there. How to deal with those? How effectively you can transmit your required information to the required users, apart from unauthorized users, without any leaky information in the wireless channels. That is also one important research challenge you can able to address. Most importantly, novel things they are addressing are channel estimation, prediction of channel, resource allocation problems. So how we can assign power, bandwidth, the number of available channels to the number of users. So these are the available research challenges with respect to this new kind of system model. And this is the basic procedure to continue those things. These are the simulation parameters. So this is an example of ambient intelligent system model. So we continuation of the morning topic. So those who want to continue their research, you can continue with this. Or you want to do some modifications, you can able to do the kind of modifications we can. And as an example of industry also, industry 4.0, all kind of machinery can be converted into cyber physical systems. Can simply make a loop, a machinery to machinery loop. So we can able to monitor that machinery working, we can able to control, monitor, we can communicate the same type of information to the external world also. External world also. That is also possible. So if you have any doubts, we can ask.
Hello. Hello.
Yes, ma'am.
Hello, sir. Sir, I just want to know more about the energy harvesting. That
Yes, ma'am.
because some
There are two protocols in Swift technology also, ma'am. Power splitting and time splitting. That means how much time a node can save energy based on the time factor. You can assign some energy to the node. Otherwise, based on the power. Suppose the source transmitting with a fixed amount of power, 5 dB power, you are sending with the information signal. Within that, a portion of the signal, maybe 2 dB or 3 dB, you can assign as a harvesting, and remaining portion you can just send as it is to the destination. So power splitting protocol having mathematical expression, time splitting protocol also having a mathematical expression. Those two factors are variables of two different factors. One is the power allocating factor, time allocating factor. If you optimize those parameters, find out the proper value of that parameter, that is sufficient to harvest the energy. This is mathematical and simulation model. Those who are dealing with the circuits, so they can implement harvesting circuit elements in the circuit itself. So as a communication engineer, we are dealing with the mathematical analysis and simulation point of view with mathematical model, not with the circuit parameter model. Are you getting me?
okay, sir.
You just get to know about this power splitting protocol and the time splitting protocol. These two protocols are there. These two are aiming for energy harvesting only mathematically. You can implement them in simulations also. Yes, please.
So, is there any possible to show one case study in the draft?
I have in my PPT also. Actually, I have completed literature survey also. Up to now, what possible amount of literature was done, case study in these three technologies: cooperative communication, normal technology, and Swift technology. I have the study. I please share. I will share these slides with you. Please get into that.
Yes, it's a request to the from the organizers. They kindly provide all the uh, PowerPoint PPTs of all the sessions. It is a request to all the organizers.
Sure.
As per my knowledge in the Swift technology is not completely applied to all next generation wireless networks. In 5G, it is still under research only. We have a chance to apply Swift technology to any kind of 5G. It is massive MIMO, millimeter wave, terahertz communication, or vehicular communication, device-to-device communication.
So one more question: that is there this SWIFT technology is applied anywhere in India that which is in working
physically,
mode?
physically not in working condition, ma'am. Still, it is in test bed condition only.
Okay.
But there are different names, not advanced ones. So renewable energy, one form of renewable energy we have. That is also one example of energy harvesting, but we are doing at a little amount of energy. So even sensor node maintenance also. It's a low level of energy. They are more sensitive nodes. So there are no physical, still they are implementing the test beds only. IIC Bangalore is dealing with it, IIT Kharagpur also dealing with it. Those who are interested, just you deal with implementation of a test bed for these Swift technologies. Thank you.
Any other questions from participant side?
Kiran sir.
Hello.
Yes, please.
Sir, can you provide your mail ID and your contact
Yes, ma'am.
number?
Yes,
So in future, if I want
okay,
to,
ma'am. Okay.
yes, sir.
Kiran Kumar Gurrala. GURRAL. GURRAL. Gurrala at the rate of nitandhra.ac.in.
NIT?
Andhra.ac.in.
Okay, thank you, sir.
Okay. All the best.
Sir, shall we
Yes, ma'am.
conclude the session by
Yes,
vote of thanks? And no more questions from participant side. Shall we conclude the session?
Naresh sir, last slide, please.
Now I request program coordinator and co-coordinator, Dr. J. Krishna Chaitanya sir. Please felicitate the chief speaker, Dr. G. Kiran Kumar.
Naresh or Babu, please.
Sir, 1 second.
Sir, good afternoon, sir. Kiran, sir.
Good afternoon, sir.
Sir. So thanks for your acceptance of our request, sir.
Thank you,
And
sir.
in one day itself, you accepted our request. Thanks for that. And I think we have seen very some unique information from you today towards the research problems and others. And thank you for that also, sir.
Thank you, sir.
And we honor with some token of appreciation from our end, sir. So virtually we are doing this. So please accept this virtual
you, sir.
felicitation, sir.
Thank you, sir. Thank you.
And now the final proceedings handed over to Sri Lekha or Harini towards the final links for day links.
Yes, sir. Thank you, sir. Dear participant, both the links for feedback and assessment are there in your chat box, and we'll share them through WhatsApp and also to your mails. Please fill them by 5 p.m. Thank you, sir.
Okay, madam. So thank you one and all for joining the session for today. And there is a one announcement for tomorrow. So we have final grand test is there on tomorrow from 2 to 3:30 p.m. So 2 to 2:45 is the valedictory, and 2:45 to 3:30 is the grand test time. So that links and everything we will provide you tomorrow, and all the participants needs to participate in it. And again, once again, we are reminding you the eligibility for getting the certificate is 80% of attendance and 60% of marks, including day-wise assessments and final assessments. So these are the two things which we are reminding you once again. Please adhere to those two. And the final proceedings for today's vote of thanks, I am proposing Jay Lakshmi Madam to take the further proceedings and close the session for today.
Okay, sir. Thank you, sir, for your valuable information on this session, like cooperative relaying and NOVA technologies and technologies. And sure that the audience got enlightened. Once again, I thank everyone. And again, the tomorrow session, again join us with tomorrow at 9:30 p.m. Thank you all.